Welcome viewers to the third segment of the seventh lecture for the online series of lectures for the course of differential geometry. In this segment, we are going to start with the regular level set theorem. So, in the previous segment, towards the end, we proved a theorem which we call Theorem 1, where we started with a function g, which is a map from a manifold n to the manifold of real numbers, and there we showed that if S is equal to G inverse of C is a regular level set of G of level C, then this S is a regular submanifold of the manifold N of codimension 1. Okay, so the next step is to extend this result, the result of theorem 1, to a regular level set of a map. Instead of a function g from n to r, we'll take the regular level set of a map between smooth manifolds. Okay, so let me state this theorem, which will be our theorem 2, which we name regular level set theorem, a generalization of theorem 1. Let f from n to m be a smooth C-infinity map of manifolds. We know what it means by a smooth map between two manifolds with dimension n being equal to small n and dimension big M is equal to small m. Then a non-empty regular level set F inverse of C, with C being a point in the manifold M. This guy is a regular submanifold of the manifold N of dimension n minus m. Okay, so you see that we obtained theorem 1 from theorem 2 by taking m to be the set of real numbers. Okay, in that case, small m is equal to 1, and and C can be any point here in the set of real numbers, and we see that we obtain theorem 1 from theorem 2 as a special case. Okay, so let us prove this second theorem. Theorem 2. Choose a chart v comma psi, which in terms of local coordinates reads v comma y1 comma y2 all the way up to yn. So this is a chart of manifold M centered at C. Okay, what does it mean? It means that psi of C is going to be the zero vector in the m-dimensional Euclidean space. Okay, so this is what we mean by the chart v comma psi being centered at C in M. Okay, then inverse image of V under F is taken to be a smooth map between these two manifolds, right? And C is a point in M. And we know that this is a regular level set of level C. We need to prove that this guy is a regular submanifold of this manifold, the domain manifold N. Okay, so now where is V? This V is an open set here in this target manifold M. And inverse image of V under F is open in the manifold N. Why? Because F is continuous. And it contains inverse image of C. Okay. Also, in this inverse image of V under F, F inverse of C is equal to F inverse composed with psi inverse of the zero vector, right? Because of this. And this is nothing but psi composed with F inverse of the zero vector, which follows from elementary identities of set theorem. Okay, so we read this as the inverse image of psi composed with inverse image of the zero vector under the map psi composed with F. Okay, hence the level set F inverse of C of level C is so from this we see that this level set is the zero set of psi composed with F. Okay. Now denote by Fi is equal to Yi composed with F. Okay. These are the M coordinate functions. Okay. So we denote this guy yi composed with f by f of fi, and from what we have studied in lecture 4, we know that this is nothing but Ri composed with psi, because psi is this homeomorphism. Ri composed with psi composed with f. This is yi composed with f, where Ri's are the standard Euclidean coordinate functions. Okay. Which picks up the ith component of an n-tuple from the Euclidean space. Okay, so this is nothing but Ri composed with psi composed with f, with HFI being a map from inverse image of V under F to the set of real numbers. Okay, good. Now, for each I in this set, finite set, 1 to all the way up to M, okay, so for each I in this finite set, Fi of F inverse of the singleton C is equal to, we know that Fi is equal to Ri composed with psi composed with F, and that acts on F inverse of C. So this is equal to Ri composed with psi of C. And we know that psi of C is the zero vector in the m-dimensional Euclidean space, right? So that this is equal to Ri of the zero vector. So the zero vector in the m-dimensional Euclidean space is an m-tuple with each entry being a zero, right? So that if we pick up the ith component, that's going to be zero as well. Good. Now suppose Fi of B is equal to 0 for all I, okay, all I here, for all I in this finite set, with B is not in this level set. Okay. Okay. Then, if this is the case, then we are going to result in a contradiction out of it. So Ri composed with, so we are replacing the expression of Fi here. We know that Fi is equal to this, right? So Fi is Ri composed with psi composed with F that acting on B is equal to 0, where F of B is not equal to C. Why? Because B is not in the inverse image of C under F. That's why F of B is not equal to C, resulting in psi composed with F at B is not equal to psi of C. And we know that psi of C is equal to 0, right? From here. And this means that Ri composed with psi composed with F of B, right, is not equal to 0 for some I in this finite set. Since psi composed with F of B is not equal to the 0 vector, at least one of its component will be non-zero. Okay, but we have seen that this is equal to 0 for all I, so this is a contradiction. Okay, so what did we arrive at? It means that F inverse C is the maximal common zero set of these smooth functions F1, F2, all the way up to Fm on F inverse V. Okay, remember each Fi is a map from inverse image of V under F to R. Okay, so F inverse C is the maximal common zero set of all these functions. Good. So there cannot be anything bigger than F inverse C. Okay, that will be the common zero set of all these M functions. Okay, good. So now let me erase this part. Since, okay, now let me draw a picture for what's happening. So this is the picture of our domain manifold N, and this is the smooth map F from N to the target manifold M. So C is a point here, and V is an open set here containing C. and this is the open set in N, which is the pre-image of V under F. So these contains the level set F inverse of C, and P is a point here in F inverse of C, and U is, so we'll see that we'll take U to be an open set containing this point P. Okay, and now there is this Euclidean space out to the M, whose origin is here, the zero vector, and there are this coordinate axis, all these coordinate axes of R to the M, and this is the set psi of V, okay, the image of the open set V under psi. Good. So this picture describes the fact that the level set F inverse of the singleton C of F is the zero set of, so this is psi, so the zero set of this composed map, psi composed with F. Okay, now since by hypothesis the regular level set F inverse of C is taken to be non-empty, taken to be non-empty by remark to the definition of a regular level set. Definition of a regular level set, which we discussed before. Dimension of the domain manifold has to be greater than the dimension of the target manifold. That is, n is greater than or equal to m. Now, fix a point P that we are doing here. Fix a point P in this regular level set F inverse of C, and let u comma phi, which we can write in terms of local coordinates as u comma x1 x2 all the way up to xn, be a coordinate neighborhood of a point P in N. Okay. Contained in, we want this open set U to be contained in this open set inverse image of V under F. Okay, we want U to be contained in this open set. Okay, F inverse of V. So since F inverse of C is a regular level set, by hypothesis this is a regular level set. Since this is a regular level set and P is in F inverse of C, P is a regular point of F, right? P is a regular point of F. So what does it mean? From the definition of regular point, we know that the differential F star comma P at P is surjective. Okay, so we'd see that the differential F star comma P of this smooth map F at the point P is going to be surjective. So let me erase this part. I want to keep the picture intact. So F star comma P is a linear map from this tangent space TPN to the tangent space TFPM, right? This is surjective. That is, the rank of this linear map F star comma P so this is surjective means that the image here is the whole thing, right? So the rank of F star comma P is the dimension of the image of the vector subspace here, right? And that is precisely the rank of this linear map. And we know that since the image coincides with the target space, therefore the rank of F star P is going to be the dimension of this tangent space, which is dimension of this tangent space TFPM, and this is equal to M, right? So that is rank of the Jacobian matrix DFI del Fi over del Xg evaluated at P. Okay, it's a matrix where I runs from 1 to M and J runs from 1 to N, right? This is an M times N matrix, and I want the rank of this M times N matrix to be equal to M. This is an M times N Jacobian matrix. Okay, good. Now by renumbering f i's and x j's. Okay, we may assume that the first m times m block of this matrix, Jacobian matrix, del f by I by del xj, evaluated at p, ij runs between 1 and m. Okay, so we are taking the first m times m block. We are renumbering fi's and xj's according to our convenience. And since the rank of this Jacobian matrix is equal to m, we can renumber them, renumber these fi's and xj's conveniently, so that the first m times m block is non-singular. Okay, in other words, the determinant of the first m times m block is going to be non-zero. We can always do that because the rank of this Jacobian matrix is equal to m, right? Such that the first m times m block is non-singular. Good. Now, replace the first m coordinates of x1, x2, all the way up to xm. Sorry, the first m coordinates x1, x2, all the way up to xm of the chart. Remember the chart u comma phi, which was u comma x1, x2, all the way up to xn. And we have seen earlier that that n is greater than m, greater than or equal to m. Okay, so it's something like x1, x2, all the way up to xm, then xm plus 1, xm plus 2, all the way up to xn. Okay, so there are n minus m such entries here. Okay, so in these n coordinate functions, we replace the first m coordinate functions, that is x1, x2, all the way up to xm, by f1, f2, all the way up to fm. Okay, remember, p is in u. Look at this figure. P is inside this open set u here. Okay, now what is the claim? The claim is that let me erase this figure now. Now the claim is that there is a neighborhood u sub p of the point p inside the open set u, such that u sub p comma f1, f2, all the way up to fm, and then the remaining coordinate functions xm plus 1 all the way up to xn is a chart in the atlas of n. Okay. Okay. It now suffices in order to establish the claim to compute the pertinent Jacobian matrix at the point P. Okay, so let me do this. So here del fi is this block del fi over del xj, and then I have del fi over del x beta. Now here del x alpha over del x j, and then here del x alpha over del x beta. Okay, so how many rows are here? Here there are m rows. Okay, I runs from 1 to m. There are m rows, and there are n minus m rows here. Okay, so there are n minus m rows here. Alpha varies between between m plus 1 and n. Okay, so I varies between 1 and m, and alpha varies between m plus 1 and n, right? Okay, so altogether there are n rows here in this matrix. Okay, now what about J? So let's take the columns. So J varies between J varies between 1 to m, okay, m columns, and again beta varies between m plus 1 and n. Okay, and this is del fi by del xj, and this is some unknown. So this is a zero matrix of size what? N minus m times m, right? And this is also and this one is an identity matrix, right? Of size n minus m times n minus m. Okay. So only the diagonal entries in this block are going to be 1, and elsewhere they are going to be 0. And this is a 0 matrix of this size. Okay, good. So what is the determinant of this matrix? The determinant the determinant of the matrix above is equal to that del fi by del xj at p, right? And we renumbered fi's and xj's in such a way that this is non-zero, remember? So this is non-zero since this block is non-singular. Now, using that important corollary, using the important corollary to inverse function theorem that we used while proving that the two-dimensional sphere is a regular submanifold of three-dimensional Euclidean space. It is guaranteed that there exists a neighborhood U sub p of p in N such that there is a coordinate neighborhood U sub p, and the first m coordinate functions are going to be f1, f2 all the way up to fm, and the remaining ones are x to the xm plus 1 all the way up to xn. So there exists a coordinate neighborhood of p in N. Okay, and in this chart U sub p f1 f2 all the way up to fm comma xm plus 1 all the way up to xn. In this chart up intersected with s defined as the level set f inverse of c is defined by the vanishing of the first m coordinate functions f1, f2 all the way up to fm. Why? Because we proved earlier that S is the maximal common zero set of all these m coordinate functions, all these m coordinate functions f1, f2, all the way up to fn. We have proved it earlier. Okay, so nowhere else, we have seen that nowhere else in U sub p except for this level set f inverse of c, these m coordinate functions f1, f2, all the way up to fm identically vanish. Okay, therefore U sub p comma f1, f2, all the way up to fm comma xm plus 1 all the way up to xn. This is an adapted chart. For n relative to s. Since this is true for every p in s, which is equal to f inverse of c, f inverse of c is a regular submanifold of n of dimension n minus m by proposition 1 that we proved in segment 1. Proposition 1. Okay, QED. Good. So we have successfully proved regular level set theorem. Now there is a useful lemma that we are not going to prove, that follows from the proof that we have done for a regular level set theorem. Okay, so let me state this lemma. Lemma 1. Let f from n to r to the m be a smooth map on a manifold n of dimension small n, and let S be the level set f inverse of the zero vector here. That is, S is the zero level set of this map F. If relative to some coordinate chart u comma x1 comma x2 all the way up to xn. Okay, this chart is about p in s. Okay, so if relative to some coordinate chart, this about p in s, the Jacobian determinant del f1 f2 all the way up to fm over del xj1 xj2 all the way up to xjm is non-zero, with j1 j2 jm being m integers from this finite set 1 to all the way up to n. Then in some neighborhood of p, one may replace xj1 all the way up to xjm by f1 f2 all the way up to fm to obtain an adapted chart of n relative to s. Okay. All right. Now a remark to the regular level set theorem that we proved a while ago. Remark to the regular level set theorem. The regular level set theorem gives only a sufficient condition for a subset of a manifold to be a regular submanifold. It's not a necessary condition though. Gives a sufficient but not a necessary condition for a subset of a manifold to be a regular submanifold. Okay. So let me state the sufficient condition. If the subset is a regular level set of some smooth map, okay, of some smooth map, then it is a regular submanifold. Okay. But there can be a regular submanifold that is that fails to be a regular level set of some smooth map. Okay. So, but there can be a regular submanifold that fails to be a regular level set of some smooth map. Let me provide an example supporting this argument. Take F to be a map from R2 to R, defined by f of x, y is equal to y squared. This map is evidently C infinity, and the zero set z of f is the x-axis, right? F of x comma 0 is equal to 0. For any value of x, we are going to have f of x comma 0 to be equal to 0, so that the zero level set of this function is the whole x-axis. And the whole x-axis is a regular submanifold of R2. The x-axis is a regular submanifold of R2. Okay. However, observe that del f over del x is equal to 0, and del f by del y is also equal to 0 on the x-axis. Okay, what does that mean? By proposition 9 of lecture 6, all the points on the x-axis are critical points. Every point of z of f, that is x-axis, is a critical point of f, right? Thus, although z of f is a regular submanifold of R2, it is not a regular level set Okay, it is not a regular level set of f. Okay, good. It gives us an example elucidating the fact that these condition this regular level set theorem that gives us a sufficient condition only for a subset to be a regular submanifold of a given manifold. It is not a necessary condition. Okay. Now, an example of a regular submanifold. Let me erase everything. An example of a regular submanifold. Special linear group. Okay, which we denote by SLN, R. It is a subset of the general linear group over R. It consists of n times n real matrices with unideterminant. Okay, we know that any matrix here in GLNR has determinant non-zero, has non-zero determinant. Now we impose the condition that the matrix has unideterminant. It is non-zero, but we want it to be 1, the determinant to be 1. So all such matrices form a group called the group of, it's called the special linear group of dimension, special linear group over R. Okay. So it is easy to check that the set forms a group. The product of two matrices with determinant with unideterminant is again a matrix with unideterminant, and the inverse of a matrix with unideterminant is again a matrix with unideterminant. They follow from these two identities. Determinant of A times B is equal to determinant of A times determinant of B, and determinant of A inverse is equal to 1 over determinant of A. Okay. So this way we verify that SLN, R is a subgroup of GLN, R. Okay. Now let F from GLN, R to the set of real numbers be defined by f of A is equal to determinant of A. So notice that F is a smooth map, and SLN, R can be seen as the inverse image of 1 under F. Okay. So F is this map from GLNR to R, and the inverse image of 1 under F is a subset of GLNR, which is precisely SLN, R. We'll now check that check that 1 is a regular value of the smooth map F. That is, the matrices in this set, inverse image of 1 under F, are all regular points of F. This is what we need to see. Okay, let Aij, where ij runs from 1 to n, be the standard coordinates on the set of n times n real matrices over R, and let S sub ij be the submatrix of the matrix A in R to the n cross n. Okay, so Sij be the submatrix of A formed by deleting the ith row and the jth column of A. Okay, so this is how we form this submatrix Sij. Then denote by Mij of A the determinant of this submatrix, okay, which is called the minor of the ijth minor of A, which is a number. The I comma j minor of the matrix A. One then has f of A is equal to determinant of A is equal to, so we pick up the ith row of this matrix A and write down the determinant using this ith row of the matrix A, which reads I minus 1 to the I plus 1 AI1 MI1 of A, then plus minus 1 to the I plus 2, so I2 entry, AI2 MI2 of A, plus finally minus 1 to the I plus N AIN MIN of A. That's equation number 6. Therefore, del F by del A ij of A, okay, is equal to minus 1 to the I plus j a, sorry, I'm deriving things with respect to aij, so that I will just have mij of a. That's equation number 7. Okay. Now, by proposition 9 of lecture 6, 9 of lecture 6, a matrix B in GLN comma R will be a critical point of this function f, which is a map from GLNR to R, defined as f of a is equal to depth a if and only if all the partial derivatives, all the partials del f by del a I j with respect to the n square coordinate functions aij vanish at b in GLNR. Okay, that is, we want del f by del aij at b to be equal to minus 1 to the I plus j, right? M sub ij of b to be equal to 0. This is what we want. Hence, our matrix B equal to, whose entries are small b sub ij, so B in GLNR is a critical point of f if and only if all the n minus 1 times n minus 1 minors of b, that is mij of b, all these minors are 0. Then by equation number 6, so what was equation number 6? Equation 6 was the expansion of the determinant along the ith row. So according to equation number 6, f of b is equal to minus 1 to the I plus 1 bi1, right? mi1 of b plus all the way up to minus 1 to the I plus n bin min of b. Okay. And since all these minors are identically 0, this is equal to 0, which is the determinant of B. This is equation number 9. Since every matrix in the subgroup SLNR of GLNR has determinant 1, no matrix in SLNR can be a critical point of F. In other words, all matrices in SLN, R are regular points of the function f, regular points of f, and f inverse, this is a regular level set. F inverse of 1 is a regular level set. Now, by the regular level set theorem, which gives us the sufficient condition for a subset to be a regular submanifold, according to that theorem, SLN, R being equal to this regular level set is a regular submanifold. Regular submanifold of GLN, R of codimension codimension 1, right? That is, dimension of SLNR is equal to dimension of GLNR minus 1. And we know that the dimension of GLNR is n square, because this is an open set of R to the n square. An open set of a manifold is a manifold of the same dimension, right? So GLNR has dimension n squared, and SLNR has dimension n squared minus 1. Okay. All right, that's it. So let us end the third segment here. We'll be back with definition of the rank of smooth map and relevant results in the fourth segment. Thank you for attending this third segment of the 7th lecture.